Let me pull it. All right, we have our distinguished lecturer now. Let me introduce to you Pavel Safronov, who is from University of Edinburgh. Pavel was a student of David Benzie in U, Texas, and he's an expert in supersymmetric geometry, and so he will enlighten us today on Donaldson-Thomas invariants of 3-manifolds. Pavel?
Yeah, thanks. Okay, so yeah, I want to explain this kind of new field of Donaldson-Thomas invariants applied, which are usually applied to Cohomological threefolds. I want to apply them, construct them for 3-manifolds. So these are some kind of interesting 3-manifold invariants. And in today's talk, I'll just set up some background, and then I'll get into more details very soon. But let me begin with some motivation. The goal for today will be to make sense of the following situation. You have a function, maybe a real value function on a manifold, and you want to define something like Morse homology, and I'll say a bit more about that. Of F. And this is something that's well defined. If M is compact, and there was the closed. But often, if you look at statistical examples, we're interested in cases where M is not compact and non-compact in a very strong sense. So we're interested in the case when M is actually infinite dimension. So the two interesting examples from physics that you might be familiar with so some related to the talks earlier today. You look at some symplectic manifold. And as your manifold, we look at the loop space. And in this case, there's something maybe possibly with some potential with the function. In this case, on the space of loops, there's a natural function that's called the symplectic action function. Space. And the Morse homology of the symplectic action functional, if you interpret it suitably, is either symplectic homology or quantum homology, depending on the precise setting. Of this symplectic manifold. Okay, so that's an interesting example where you can make sense of Morse homology, but for this you need to do some extra analysis. Here's another interesting example. So let's actually say n is some closely related 3-manifold. The some compact group. So maybe think about G being SC2. Then you can look at the state of connections. And so this is the state of connected G connections modulo H on the 3-manifold. So principal G bundles. With connections. And modulo H. And then in the space of connections, there's a Chern-Simons functional. So maybe it's not quite usually R values. It's not some indeterminacy. G-tradition explanations say it's R mod Z value. This Chern-Simons functional. Well, let me stress that here I'm talking about the space of all connections with some infinite dimensional space. Here I'm talking about the loose space, infinite dimensional space. And I want to talk about Morse homology of this. And so the Morse homology of this Chern-Simons functional. You can actually make sense of this, at least maybe in the case of SC2. This is instantaneous homology. So this is some interesting invariant of 3-manifolds. And again, informally, to think of this as Morse homology, but since it's an infinite dimensional manifold, Morse homology by itself doesn't make sense. Okay, so I want to consider the case, really it's going to be a slight variant of the second example, but for which analytical tools are not available. But there are some totally different tools that can be used to make sense of this Morse homology. So in this case, G is a complex Lie group, or maybe let's say complex algebraic group. So for instance, you can think about the group being SLGC. And so basically, Morse homology is what I'm going to be talking about today in the first SLGC case or in the general complex algebraic case. So the reason it doesn't quite work analytically is that there was something important here that I was looking at compact groups. So you have some control. Here I'm talking about complex algebraic groups, so SL2C, which is not compact. They don't have relevant analytical tools. And so you can't use the same tools as used in part 2, but there's nothing special in this case that everything is in the world of complex algebraic geometry, so you can actually use complex algebraic geometry to make sense. So then
just restate that slide.
pardon me?
Just a little bit small, you restate that slide.
Yes, so just maybe just the point is that G is not compact here. So the reason we have some good control in the system Florian homology case is that we talk about SC2, which is compact, while also the C is not compact. So you can't define it in the same way. Okay. So next I want to just give some flavor. There's some kind of understanding of what this Morse homology is. And I'm going to give different versions of this homology theory. They're both going to be equivalent in various ways. I'm going to be in class what I mean by homology. I'm going to mention the 3 or so equivalent definitions for guidance. Okay, so let me begin with the simplest version. So let's say for now is just an actual manifold. And let's take alpha to be some closed one form.
Still real one.
Real magnitudes. Like this is smooth manifold. So let's take manifold in the plus one form, and I'll be working on these numbers. So let's look at the complex of differential forms. But the differential that I'm going to consider is the drum differential plus vector in this one form. That's sometimes called just drum complex. So that's one version of this kind of Morse homology. If you look at this homology of this drum complex, let me give a slightly more topological flavor, which doesn't rely on the fact that about manifolds. Okay, so I can think about this one form as defining a class in the first homology. Okay, this class, you can think of this as a one-dimensional local system of coefficients that I'll just write theta alpha. And so you can actually, let me just maybe call this H. Because the drum theorem tells you that homology of the Swiss drum complex is the same as homology of M, not with C coefficients, but with coefficients in this local system. Okay, so now let's look at variants of this where we deform alpha. There's the following nice result. I think it's originally canonical. But there are some further works by Farber and other people. Okay, so this right-hand side homology of M, this is just, let's say, singular homology with local covariance. This can be defined from homological spaces. So let's just say M is some finite W complex. Alpha is some homology class. Actually, let me take it to the integral. And okay, so you can look at cohomology of M with local system coefficients where you deform this local system by tau alpha, where tau is some something defined in C over 2 pi I Z. So the point is that if you shift it by 2 pi I, this local system will not change. And the claim is that this cohomology group is actually independent of tau away from finite remaining points. So even though this seems to depend, this homology depends on alpha in a very explicit way, the claim is that there's some specific points where there's something interesting happening with this homology, but away from those values of tau, this scheme of Z, this homology is actually independent. So that's the kind of homology I want to consider. I want to consider the kind of generic homology.
Is this for every tau?
So you look at the set theme of 2 pi Z of all possible taus, and then you look at this vector space, which depends on tau. The claim that away from finally meaning points in the set, this vector space that will come from.
It's something like generic vanishing in a complex world, like.
Something like that, yeah. It's something like if you're familiar with Morse homology, it's there's no interesting gradient flow lines in certain cases. That's one thing you can do. So I would consider this kind of homology for generic. Okay, so let me just maybe somewhat quickly mention this approach, more classical approach, Morse homology. In this case, it's called Morse-Logical homology. So let's say N is actually a Riemannian manifold. And you have a function which is not real valid function, but circle valid function. So for instance, if differential will define the cost in cohomology, something like this. Okay, so in this case, you can consider the universal cover. So there's maybe a real valid function, or maybe a certain cover, certain z cover. And then you can consider a certain complex. So let's say it's a C module generated by critical points. It happens to be a module over the ring of Laurent models just because you have this active back transformation. So this is not quite the right complex. You have to slightly localize it. And you just take this module and tensor it with Laurent series T. So this has a differential. Counting gradient flow lines. The function. Yeah, I have to say that this is one function. And then, so this is known as the Novikov complex. And so Novikov proved that the homology of this complex is actually the same as this generic homology. So this is something defined over C. Extend because that's another way to define kind of Morse homology. So there was this kind of topological definition. There was this analytic definition. Now I'm going to say a complex algebraic definition.
Sorry, may I ask you, so these finitely many points where it jumps, is there some interpretation? Or
I'm not sure. So this corresponds to actually looking at the homology of M rather than before you do localization. So if you do this localization, you can actually get rid of that norm. And then it's not going to be flat over this string. But then you just turn, when you localize, this is the field. So all right, so here's another version. So let's say M is a complex manifold now. And F is a holomorphic function. So in this case, you can define what's called the sheaf of vanishing samples. So this is actually a complex of weeks. We can confirm that. So this is actually a perverse sheaf on the zero locus. Let me maybe just, let's say 0 is the only critical value. It's a perversity on the critical locus. The critical locus of F is just the set where the diffraction happens. Okay, so there's this natural sheaf in this associate. And so how does this sheaf relate to what I was talking about before? There's this interesting theorem due to Safronov, which says that you can actually relate this sheaf to the fixed ground complex. And the cohomology of this sheaf of vanishing cycles. So let's say this is something again defined over C. I'm going to extend scalars from C to Laurent series in some variable, I'll call it bar, is actually the same as cohomology of the sheaf, which is the Piston-Dron complex. Again, the Piston-Dron complex, I'll look at the version over H bar, and the differential is H bar D plus, yeah, right. We can look at this complex of sheaves, and its cohomology coincides with the cohomology of the two vanishing cycles. If you extend. Okay, so the thought here is that if you're in this complex situation, you can model this generic homology, called homology or Morse homology. By computing homology of the sheaf vanishing cycles.
Just one question, because now you are always supposed that 0 is the only digital value.
Yeah.
Okay? So all in all, it doesn't matter that it's the 0, but you won't have to have one critical value. So how restrictive is this? Like,
It's not restrictive at all. So if you look at a function restricted to the critical locus, just because of this equation, the function is constant. What are the constants? So actually, they're just components of the critical locus where the function has different critical values. So you can just allow yourself to localize to some open subsets for components. The critical locus, you can just shift the function so that zero is the only critical value. So it's not restricted, it's just to slightly simplify the. Okay, so this is essentially what I want to use, this cohomological matching cycles. And the other problem is it's still not completely well defined in the case I care about. So again, let me go back to the example. So my manifold, my infinite dimensional manifold, is the space of connections where G is some complex operating group. And my function was the Chern-Simons functional, maybe Z. The sheaf of management cycles is not defined in this situation. It's only defined when you actually have a finite dimensional complex manifold. But there's something nice about this situation, which is let's look at the critical locus of this Chern-Simons functional. This critical locus is the space of flat connections. And let me just write it as log G of n. And you can identify flat connections on the manifold with representations of one another. On conjugation. Now, the space of all connections is some infinite dimensional space, infinite dimensional manifold. But if you look at this expression, it's something extremely nice. The fundamental group is a finitely generated group. So this space of homomorphisms from fundamental group into G is actually a finite dimensional algebraic variety, possible singular. And then it model out this variety by an acting group. So this is something that lives in the finite dimensional world. Namely, this is a singular complex algebraic stack. So the fact that the stack is not so important is really just, I want to remember the fact that it's quotient by G. But it's on a finite dimensional algebra. Yeah, that makes sense. Okay. Now the space is nice. And what I want to do is I want to define. So the space was obtained by critical locus of some function. So you would expect there to be this sheaf of magic signs. So I want to explain how this is defined. So for this, I will use extra structure on this complex algebraic step, which is called the decritical structure. So D stands for derived. And this is a notion introduced by Joyce. So let me just briefly sketch the relevant definition. And also to simplify this explanation, I'll just ignore the fact stack. I'll just be talking about either schemes or manifolds or homological spaces. So let's say X is some complex analytic space. Or complex scheme. So in this case, you can define a certain natural P. That's what you have defined. It calls Fx. So let me explain how to think about this sheet. So X is something singular. So if you embed X into something smooth, as a closed subscheme, you can define this sheet in the following way. It's going to be a kernel of functions of y modulo the ideal of x squared. So you can first you can mod out by the ideal, you can define this next. There's a derived differential to one forms. Again, define the modulo the ideal. And you can just take a kernel of that. So what I'm saying is that I'm remembering a little bit of like extra information. I'm remembering functions on the smoothing and that x and y. I remember functions, but I don't really remember the one jet. Explains that this is actually something that's canonically associated with any complex space or complex scheme. Doesn't happen. Well, some kind of functions that live in this kernel are just constant functions. So you can actually split out the copy of constant functions. So now I can finally define the differential structures. There's going to be a section of the sheet, not a lot. So that locally you can write x as the control of the function. And the section just goes to the differential of this function.
or is it called invariant? So
So you're trying to remember not just the principal locus, but you're trying to remember a little bit more information. There's a world of derived complex analytic spaces or derived complex schemes. There's also derived principal locus there. Some extra structure that I'll mention right now will give rise to the okay, so this looks like a somewhat artificial example or a somewhat artificial definition. Let me give some examples. The point is that a critical locus is something that's locally critical locus of a function, but there's not necessarily a global function which represents the whole case. Let me mention two examples. One example is just the one where it is set there. So n is a closed oriented 3-manifold. And G is a complex algebraic group. So this space, let me refer to this as the character stack. Is a decrease the locus. And another example is a variant of this. They take M to be, for instance, the smooth and proper polynomial threefold. Again, G is the same. Then you can look at the moduli space of G bundles. So hallmark of G bundles on this polynomial variety. That's again a decrease locus. So locally, you can write them as critical loci functions. Normally, here you want to think of writing this as a critical locus of Chern-Simons function, but that's an infinite dimensional representation. The claim that Zariski locally can actually have finite dimensional representations. So these two examples actually fit into slightly more general theory that I will just mention the name. There's a theory of symplectic structures on possibly singular or maybe derived algebraic stacks. And so this was introduced by David Sotsy. Under the name of supersymmetric structures. And so both of these spaces actually have this kind of shift symbolic structure. It's a minus one shift symbolic structure. And then for any for a scheme with a minus one shift symbolic structure, around the same pillars, prove that these are different pools. So locally, there's kind of a Darboux type theorem in the shifted symbolic context that says that anything minus one shifted symbolic is locally first to locus. Pretty much all reasonable examples of different loci, they all come from this more general theory of shifted symbolic.
So what is the role of 3-dimensional? Because this shifted works for local system.
Yeah, so shifted symbolic structures can be defined. You can put in a number here. If you want to have decreasable structures, that's where minus one is important. And this is why, so minus one in this case is 2 minus 3. So this 3 is this 3 and this 3. You can look at close range 5 manifolds, for instance. In this case, they will have a minus 3 shifted symbolic structure. But there's again a Darboux theorem, but it's not a first locus. Any other questions? Okay, so all right, so I'm still talking about decreasable loci. So now I want to explain that decreasable loci have this sheaf of vanishing cycles. So locally, they're given by critical locus. So on the critical locus, you have 2 vanishing cycles. And what you want to do is you want to glue those sheaves on local models. It's almost possible that there's slight complication, which is actually quite interesting, which I want to mention. So if you have some decreasable locus, you can define what's called a virtual canonical bundle. So I will not define it in general, but let me just explain what it is in the 2 examples. So this is some singular scheme, so you can't just take the usual canonical bundle. So these are not given LCI. But this virtual canonical bundle, for instance, for the multiplied bundles, fiber of this virtual canonical bundle at the bundle P is just the determinant of the cohomology of that given bundle. And same thing for local systems. So if you think about what are what is the tangent bundle of the moduli bundles? Well, you want to say that the formations are given by H1, but then there's obstructions given by H2. There are further obstructions given by H3, and then automorphisms is given by H0. And if you can take the determinant of this complex, it can be this line, and kind of what you expect is true, so that line is exactly this virtual canal. So, so the reason I want to mention virtual canonical bundles is that there's this important notion of orientation. It's just a choice of square root of this canonical bundle. So you have some complex line bundle, and you want to choose a square root. So the square root might not exist, so not every decreasable locus is orientable, but the choice of the square root is the orientation. And the reason I mentioned this is that once you choose an orientation, so let's say X is an oriented decreasable locus, the work of Roth, we see on Android. Before they find a perverse sheet, or you can enhance this to a mixed odd model. So you can talk about weights of the Hodge structure, for instance, on this decreasable locus, which is locally just the sheet or mixed Hodge module of finite cycles. If you're familiar with this sheet of magnetic cycles, the sheet of magnetic cycles also has a monogram operator, monogram of magnetic cycles, and there's also a monogram operator. So it's quite a rich structure that you get on the decreasable. And so the reason I'm talking about this sort of sheet is that we can now define a spectral kind of homology of this of the oriented decreasable locus. So this distribution essentially goes back to concentric children. And others essentially goes for that children. There's this notion of critical cohomology. This homology of the sheet. So let me just mention one very easy example where this just reduces to the usual homology. So I was talking about complex analytic spaces or complex schemes, but let's consider the case where X is actually smooth. What is yes, yeah, that's so let's say X is just some smooth scheme or a smooth manifold, complex manifold. In this case, it has a unique decryptable structure. And in this case, the sheet, this reverse sheet I'm talking about, is just a constant sheet. It's the shift to making it reverse sheet. So then, in this case, this critical cohomology is just actually the usual cohomology and possible. More than less.
That's a bit tricky here. So what if X is smooth, but it has no multiplicity?
You mean non-reduced?
Yeah.
Yeah. So if X is not reduced, when I say smooth, I mean reduced, smooth in the sense. Yeah, if it's not reduced, then there might be different structures.
I mean, the more multiplicity.
Yes, so I think if a decryptable locus is reduced, I believe it's automatically smooth. But I need to think about it. So all ancient examples of decryptable locus are actually not reduced. So so this is now my replacement for the sheet management cycles for decryptable locus. I can talk about homology of the sheet management cycles. Let me just end by talking about the two examples. These two examples, as I said, what you need is you need to choose orientation data. You might ask, well, is there one and how canonical it is? So let me just end with two theorems. No, first theorem. The first theorem is in the case of Cohomological 3-folds, due to Joyce and Ottmeyer. Claims that in this case has a canonical orientation data. You actually define the invariant cycles here. And this cohomology is actually what's usually called the cohomological Donaldson-Thomas invariant of the 3-fold.
How does it relate to the usual? You see,
So there's a numerical desinvariance. So numerical desinvariance is defined in a slightly more general setting. So there you don't need polynomial 3, but you could consider polynomial 3 case. The Euler characteristic okay, so you have this perversion. You can look at its local Euler characteristic. That local Euler characteristic is the Baron function. It's a certain constructible function we can define on a complex scheme. So it's really the Baron function of x. And so if you just take the Euler characteristic of x about with respect to the Baron function, that's the usual numerical constant. The Euler characteristic of this homology is the numerical constant. And so finally, in the case of 3-manifolds, we proved this with Florian Naef in the recent paper. Then is it closer to 3-manifold? So the point is that so this character stack of n has a canonical regulation. So if you think what this means, you need to define a square root. So we actually define something slightly stronger. You can define a section of this canonical bundle. So in other words, you want to define a non-zero element of this determinant of the cohomology. So we use what's called right-master torsion of n. We define this section of the vertical canonical. Our thought is that yeah, so this is a feature for locus. You have the canonical rotation data. So you can consider its homology, and that's the cohomological invariant of the triad. So on Thursday, I'll mention some example and some properties. This invariant and how it fits into various other instructions.
So is this one section that you mentioned in the skein?
No. Yeah, this is just even define this this sheet, the sheet. You need to have a section. But what we're talking about is that there's a section of the relation on top of that.
Yes.
So the instant polar homology for SU2 is ZA gradient, right? You don't have such a thing here, right? Or do you? So in a sense, it's weaker, or
the grading, I would say it's stronger. So that grading is coming from this vertical grading. The Z1A grading is the cohomological grading, and then it's not H because we have gradient flow lines which can connect points that differ by this. So that's why the grading is not as degrading, but it's a Z model.
So here you have it as well.
Here we have a Z gradient, yeah. So it's just a cohomology.
Oh, I mean in the local.
Yeah, yes. So in either setting, like in this degree to locus setting, there's a Z gradient. There's just homological gradient.
Oh, so maybe what I mean is that, so if, for example, in this brief sphere examples, there will be no